So we are the low latency camera feed development project, and my name is Rohit Karthickeyan.
I'm Ayush.
I'm Sebastian Clarke.
And I'm Brayden Casaren.
So our mission is to essentially find methods of reducing latency to a minimum in unicast cameras over a computer connection and network. So the importance of low latency connections is that there's many modern applications of this technology, such as, for example, in self-driving cars. See, if you were sitting in a Tesla and it was driving itself, you wouldn't want the car in front of you stopped. You wouldn't want your own Tesla to stop 1 second later because it might crash. So, and the other applications of this also include sports and live news and, well, security and surveillance.
So here is our project design. So we have a big cardboard box that contains our camera that's constantly recording our LED light, and the light will be off and then turn on at the beginning of every second. We also have our computer, our node, and our device that we have called the time machine, and they're all connected through the switch in the middle. So the reason why we have our camera in the box, it is sealed so no light can get into it. And the camera is constantly recording and it sends video packets to our computer. The video packets pretty much contain information that makes up the actual video. The reason why we have it dark, so we can understand when the light turns on and it starts recording that light. When the light is off, the video packets will contain information that makes up dark video. It has no light. When the light turns on, it'll start capturing packets that contain when the light is on. So when we observe on a computer and observe the payload, the data inside our video packets, when they come in, we would be able to observe when the change happens, when it switches from dark to light, and the amount of time for the camera for our computer to receive that data from our camera is the latency. Our powerhouse of our whole setup is actually the time machine. It is a device that contains a GPS, and it also uses PPS, pulse per second, and PTP, precision time protocol. PPS sends a low voltage to our LED light that turns it on at the beginning of every second and is very precise. Our GPS acts as a standard time. Like GPS communicates with the satellites orbiting the Earth, and it calculates our position on the Earth, and that's how we're able to get super precise time. And it's a standard that most devices can use and be very accurate. PTP uses that time as a standard to timestamp our video packets once they come in and once they're first received by our computer, so we know when they first came in. And it also uses that standard time to apply a delay to those video packets, so all devices that are connected together can be synchronized on this standard GPS time. And that's our actual setup. That's the little environment that we had our camera inside, and over here is our switch, and that was our node that we worked on.
All right, so an issue that we ran in during while collecting data from our actual camera is the amount of noise that it contained, as it made it extremely difficult to detect any changes that the light actually did because the noise hit it. So to simulate that, we actually created artificial videos to kind of show how noise would affect our actual camera, which would be streamed from our secondary node over we see. So we decided to visualize our data through a Python library called matplotlib. And this is very useful as it kind of helps with comparison and pattern recognition. Not to mention that each JPEG contains like hundreds of thousands of different data bytes, which would be very hard to go and scour it and find different and compare each one of them, which is why visualizing it would be better. And we kind of want to gain information on how noise would affect our packets. So we went through a couple different methods of collecting data for our histograms and how to plot it. But the one that we ended up sticking with was it plotted RGB values instead of bytes, and actually created 3 separate histograms based on each color of RGB being red, green, and blue. And as you can see, this is what the old graph looked like, and here are the red, green, and blue graphs.
So some more changes that we made is that we were able to change the camera settings for our camera to almost eliminate noise completely. And we also use FFmpeg software to get video onto one MJPEG file, and it's consistent in JPEG files. So these histograms represent the number of occurrences of red pixel values in our camera footage. As you can see, it's mostly 0 because our footage is mostly dark. However, as you saw in the previous image, there is some white light when the LED flashes on, and that's why you could see that there is a little bit of high occurrences of red value pixels. And it's also the same thing with green value pixels, where due to the white light, there could also be some amounts of green value pixels. And for blue, the number is obviously much higher because our LED is blue, it emits blue light.
All right, for actually calculating the latency though for our camera, we had to use a couple different tools, one of which was TCP dump, which let us actually collect and view the packets then afterwards in this tool called Wireshark here that you're looking at. And to actually get the video streamed for the packets though, we used FFmpeg, which would save our video onto the node. And after this, we were able to actually try to look for the packets that represented each frame that we wanted to find. The frames we wanted to find were the ones where the switch occurred, where the LED came on instead of being darkness. And to do that, we actually just looked through these packets and looked for indications of FFD8 and FFD9, which for MJPEG, it used JPEG encoding. It was just a sequence of JPEGs. And so how that worked is that each JPEG started with the sequence of bytes, which were FFD8, and then ended with FFD9, which is here. And so using that, we were able to find patterns in the packets to find when frames started and ended. And then we could basically seek out frames in the packets. But to actually find which frames we wanted to find in the packets, we used a software called VLC Media to view the JPEG images that we got from the actual video, which we deconstructed into JPEGs using FFmpeg. And then after that, we used the packets that we found and compared them with the JPEGs just as an extra measure to make sure that they were the correct packets. And we could find matches on those that would tell us that that was the correct packet, and then go back to the packets and we could actually compare the timestamps on it from PTP and compare that with the start of a second, which is when we knew the LED actually turned on, and that would be our latency. So here we have one of them. It's packet 223 was frame 18, the start of frame 18 for us, and gave us a latency of around 44 milliseconds for MJPEG. And then for actually reducing latency though, we had a couple ideas, one of which was changing the codec to H.264, which was the only other codec that our camera supported, or changing the frame rate. But unfortunately for frame rate, our camera could only operate on a maximum of 30 frames per second, and anything lower would probably lead to a higher latency because there'd be a greater amount of time between frames. So we didn't actually change the frame rate. We figured that maximum would probably be most efficient for our latency, and changing the compression amount was another thing we considered because we thought that changing the compression would lower the bit rate because there'd be less data to actually transmit, which would, if we were using up too much of the bandwidth, it would allow us to use less and reduce latency, hopefully. But the latency was fine with the default of 30. So we stuck with that. And we did change the codec though to H.264, which changes how the frames are actually saved. It does a different thing with, instead of every frame being encoded as its own JPEG, it actually has 3 types of frames, which are I, P, and B. And the I frames are basically somewhat similar to a JPEG, but the P and B frames use reference frames and motion vectors to actually compress the data a lot more. And using this codec, we calculate the latency if we just use I frames, which is similar to MJPEG, to be around 34 milliseconds, which was actually lower than MJPEG. And then if we use the actual I, P, and B frames, though, we got around 60 milliseconds, which was decently higher, but it reduces the size of the files by a considerable amount. And that is all.